Hello, welcome back to the Auto Contouring Review. This week we're going to be looking at a paper entitled An Evaluation of Atlas Selection Methods for Atlas-Based Segmentation in Radiotherapy Treatment Planning. First author on this paper is Schipaanboord, who we spoke to in a previous video looking at extreme value theory, trying to look at what the best possible performance of Atlas-based segmentation could be. This paper is a follow-on from that paper and tries to look at what the current state of the art is in terms of Atlas selection. What performance are we able to achieve using the methods that have been published previously, and how close is that to the best possible? Later in the video we'll be talking to Djamal Boukerroui, the second author on this paper, so that we can mix it up a bit and you can hear from multiple different people about their work. So this paper considers Atlas selection. We've got a patient, we've got their CT, and we then take a group of atlases, where those atlases are CTs with ground truth contours, and we want to know which atlas is going to perform best for our current patient. We want to select the best performing atlases. A lot of the published literature, however, considers how similar is the atlas's CT to that patient CT. Because we don't know the contours on the patient, we have to use the similarity between the images as a way of judging which is the best atlas. So in this paper, the authors took the approach of trying to do an exhaustive search of similarity measures. So they took all of the atlas CTs, and they treated each one in turn as a patient, and then they calculated a bunch of different similarity measures between the atlases and the patients, obviously ignoring the diagonal where the atlas is the patient. And they looked at a range of different similarity measures. So the image similarity measures which compared the images, and they could do this both after rigid registration and after deformable. So things like normalized mutual information, which really look at very much directly at image similarity. They also looked at deformation-based methods. The assumption of a deformation-based measurement is that the more similar the atlas is to the patient, the less deformation that would be required. So those are measures such as the harmonic energy or determinants of the Jacobian. And they also looked at tissue similarity measures. So this is derived from the image, where you might threshold the image to identify regions of bone. And then you could look at the DICE score, say, of the overlap of bony regions within the two images. So this is a very much a surrogate of image similarity based on regions. Having selected an atlas based off a similarity measure, we now need to know the performance. So here, taking those same registrations and those same atlas patient pairs, they could look at what happens with the contours when you transfer the contour from the atlas to the patient. And again, they calculated all of the possible combinations of the measures of performance, such as DICE and average distance. So now for any particular similarity measure, we can select the best atlases and we can look at their performance. The authors also introduced three other benchmarks. Firstly, there's random selection. What happens if we just arbitrarily select atlases for a particular patient? And in this paper, that's exactly what they did for the random selection. They picked random atlases and looked at the sort of performance they were getting. The other end of the spectrum, there's what they refer to as the oracle. What if you knew the answer when you were selecting the atlas? What if you looked, say, to pick the atlas which you knew was going to give you the best DICE score? What would that performance look like? And by looking at the oracle, we can then look back and see how close is any of our particular atlas selection methods to achieving that perfect selection. Obviously that perfect selection is not available in the clinic, but gives us a benchmark at which we can judge the other atlas selection methods. And the last sort of, benchmark that they looked at was offline selection. This is where we don't consider the patient at all when selecting atlases. If we take our pool of atlases and we look at the performance against each other, and we can select generally well-performing atlases, and then we apply those generally well-performing atlases to our patient, having never seen the patient before, taking that as a fixed set, and what the performance we would get using that approach. So what did they find? This figure takes a little bit of explaining. The two solid lines, the purple solid line sort of runs diagonally down the middle, and the green line represent two of those benchmarks. So the purple line is random selection, picking arbitrary atlases, and the green line is our oracle, what is the best we can do. And each of those shaded regions represent a different selection method. So the purple, for example, represents offline selection, but we get a range of offline selection methods depending on the performance metric we look at. So that region represents all of the possible selection methods and looks at sort of variability among them. And the blue, for instance, is the image similarity, but we can take different image similarities. So again, we get a region, whether it's normalized mutual information or sum squared difference, etc. Perhaps what makes this graph hard to interpret is we look at the performance in terms of dice, and the different organs have been ranked according to dice, so we get this sort of diagonal slope. Now we can see quite a difference at the low end for the esophagus, where the atlas selection compared to the oracle, there's quite a gap between them. But we don't see that gap against the brain, where actually it doesn't seem to matter what we select. We're always going to get good performance. So to overcome this, the authors have also plotted a graph in terms of rank. In fact, it's a normalized rank. So to get a normalized rank, the authors have looked at the rank of the atlas selected as opposed to its performance. The different organs had different amount of representation within their database, so they normalized that rank on a range of 0 through to 1. So 0 is the best atlas, and 1 is the very worst atlas for that particular organ. This means that random selection ends up being a rank of 0.5. Essentially, halfway between the very best and the very worst is what we expect to get. And the best performance is down at 0. On this graph you may notice it's slightly above 0, because the authors were looking at the average performance of the 10 selected atlases, as opposed to just the one sort of best atlas that they would select. We can see more clearly on this graph that offline selection seems to outperform the other online selection-based methods, but only goes about halfway from random to the oracle selection. This tells us in terms of how well we are performing selection in terms of rank, how close we are to the oracle in our selection quality, but doesn't tell us anything about performance. To really put those two figures that we've seen together, the authors show us this graph, where they show the performance, in this case against dice, against the atlases ranked. And because we've taken each patient over a large database, we get a range of performance depending on the patient. So this gives us the median and the standard deviation. We can see that this graph's very flat. So depending on where we are on that atlas selection curve, actually it doesn't impact the end result very much, except at the extremes. So we can see a little lip up by the oracle, and we can see a very big drop off at the end where the performance is terrible. So our offline selection, although it goes halfway to the oracle, doesn't increase the performance a huge amount. And those online selection methods, based on image similarity, actually only result in a small improvement in performance over random selection. Let's discuss this now with Djamal and get his take on the paper.
Hi Djamal, thanks for talking to me today. So we're going to be discussing our paper on atlas selection. These results to some extent disagree with the perceived wisdom around atlas selection. Were you surprised by the results?
Results, okay, there are so many results in that paper actually. So there are, as a scientist, I'm rarely surprised by results when I do research, because I'm trying not to expect things beforehand. However, as we said in the paper, there are some results that may be counterintuitive. So there are some results that we found that agrees with what was published in the literature. For example, like multiple atlas selections does increase performance in comparison to single atlases. We were expecting maybe atlas selection using local feature may be performing better than using globally and that was an expected result. However, the result that we found that online atlas selection actually performed poorly in comparison to offline atlas selection. That can be explained a little bit, but the online atlas selection performance were actually very close to random atlas selection. That was a little bit counterintuitive, and we really needed to recheck our results in order to basically say, okay, actually, yeah, that's it. That's the result that we did found.
Why do you think other studies in the past, concluded that atlas selection works if we're finding it's only better, a bit better than random?
I think I wouldn't say the main thing. One of the things that we tried to do in this study is we had a large data set, first of all, and the second thing is like we wanted to know what is the scale of performance. So we defined an oracle, knowing the ground truth, even the definition of the oracle, in order basically to have I would say a good analysis. We use different measures to define what is the oracle. So we used, for example, overlap measures, and we used also distance, like the average distance for the contours, to define what is the best performance. And these measures are used in clinical now. So this is how we can compare quantitatively what is a good segmentation in the for the clinical settings. So having defined how we're going to be, what is the best possible result for the atlas selection, that showed us actually now that online selection methods perform almost as good as random, or a little bit better than random. So previously there's a lot of literature showing that online atlas selection gives a better result than random atlas selection, and that we agree with that. However, the correlation of the atlas, of the selection of the atlas to the performance to the contour itself, that actually the similarity measures that most of people used for the atlas selection do not correlate very, very well to the performance measure. And that also was, there was some literature that suggested that previously. So if I rephrase, it's like we just zoomed a little bit on the scale of the performance, and we noticed now that actually the best selection is over there. So here we are just looking to in front of our noses somehow.
So the other papers are finding that it's better than random using surrogate measures, but they haven't looked at how far they could go with selection.
Exactly.
There's quite a lot of limitations in this study that had to be made to make it tractable. It's quite a large experiment.
Yes.
Is there anything you would like to have tried that wasn't possible for time because of time?
With limited resources, probably a lot of things. I think there were some limitations, technical limitations that we discussed, and the choices that we made, and we discussed those in the paper. The two, I would say, just out of my head now, limitation that I would think about is one regarding multiple atlas selection. So for the multiple atlas selection, we used a greedy selection method in a way that we're going to be selecting the multiple atlases. We took the best 10 atlases, but those best 10 atlases are individually, not combined. Yeah. And that has a lot of, you may think basically if you want to select a team, you're going to select teams that is complement each other. You're not going to select the two best, I would say, engineer in electronics, and after when it comes to plumbing or whatever, I mean, you can't do anything about it. However, that is not feasible if you want to stick to the standards that we define to ourselves in a way that we need an oracle. So if you want to compute the oracle for that, I just tried at that time, I remember tried if we choose 10 atlases out of 10, and if our experiment takes 30 seconds to run, to try all combinations, it's going to take us 72 years to compute. So that's not feasible. So we could go to surrogate techniques, optimizations, or manifold learning in order to structure a little bit the data set to see where we're going to be targeting our best team. We didn't want to do that at that time. Maybe it's something that we would try to do one day.
I guess if we did that,
that doesn't fit in the standard of the oracle. Yeah, it doesn't fit in the standard that we fixed to ourselves. So we wanted to compare to the oracle, and that is not going to be an oracle anyway. So we dropped that. Second thing is we only tried atlas selection that use similarity, most of the image similarity metrics. So we haven't used any methods that use machine learning or similarity metrics that are surrogate to the performance. That there's very, very few works on that, which is the first thing. The second thing, it's difficult to reproduce, but it's something maybe we can try one day.
Yeah, so that's a direction for future atlas. If you were to take atlas contouring further, that would be a direction to explore then.
It could be a direction to explore. I'm not suggesting that. It's just to have, another, I would say, reference on that paper to be complete. Regarding direction, I think probably I'm going to be suggesting something else.
What would you suggest?
I think what that research showed a little bit, for example, just the idea that local methods, although they performed poorly, but selection methods that basically use local information are better. We also showed systematically better, a little bit, but systematically better. We also showed that similarity measure that use the deformation information are better. I think there are some works that we haven't also included there in the atlas selection, because we restricted ourselves to atlas selection, atlas meaning the full image. But there are other segmentation methods that use, rather than building an atlas as the full image, but they build the atlases of parts, and they combine those parts in a better way to get a good segmentation. So that agrees with the locality. It may also reduce the number of atlases that you need. And maybe that is one of the directions that maybe future atlas selection, I would say template-based segmentation selection should go.
So starting to look at organ-wise or patch-wise.
Organ-wise, patch-wise, more likely patch-wise.
Which then I guess to some extent has overlap with the work on multi-atlas fusion and weighted fusion as well.
Yes, exactly. So exactly. So I think the technology of having one single atlas with one good registration is good. It's a flexible tool. It did improve a lot in terms of segmentation results in comparison to other model-based techniques. However, if you want to push a little bit further the quality of the results, I think you need something different.
Great.
Yeah.
Is there anything else you'd like to say about the paper? Anything that you think worth highlighting in it?
I think, what can I say? I think the reviewers really gave us a hard time because we know that we have results that might be a little bit counterintuitive. but we try to simplify the message in a way that we checked even ourselves. We worked a lot in order to check what we are saying is correct. But when we think about it, I mean, the results are not that counterintuitive, because when we think about it, the offline atlas selection showed us that why the offline atlas selection works. It does work because we use the contours. So we select the best atlases because they take into account the contours. We know the contours beforehand, so we can select what is the best atlas that is going to represent give us the best performance. However, if you have a measure that just compares to the images, you may select an image that doesn't have any contour at all. So the performance is going to be 0. The second thing that paper also showed is that there are only few very good atlases, and after the performance kind of plateaus, okay, the ranks, this atlas is still better than the other one, but in terms of performance, it's a little bit small increment. And afterwards, there is also in the tail of the distribution on the other side, there are also very, very few, very, very bad atlases.
So on the whole, atlas atlas contouring is pretty robust because most atlases do an okay job, but to find
exactly
that extreme performance takes really good selection.
Exactly, especially if those atlases were selected carefully and were to represent basically the population of patients that you are using on your daily routine.
Okay, well, thanks for talking to me today. And
thank you, Mark, for inviting me.
I'm sure we'll catch up again soon.
So does atlas selection help? I think the answer in this paper is yes, but only marginally. And certainly not to the extent one might be led to believe given the large number of publications that have looked at atlas selection in the past. However, the results in this paper do agree with more recent clinical publications, such as the paper by Neili Kim that we looked at in a previous video on endometrial cancer, where increasing the database size showed a marginal improvement, but nothing clinically substantial. So given the findings of this paper, you might ask the question, why have a number of commercial vendors implemented atlas selection in their commercial auto-contouring products? And I'm left asking that same question too. But I think this paper showed atlas selection does improve off not doing anything. However, it also showed that maybe you're better off choosing a fixed set of representative atlases that seem to perform well on the general population than you are trying to select atlases on a patient-by-patient basis. And maybe that's really what this paper offers us, is a change in mindset. Rather than saying, are we better than a previous method, or are we better than the worst we could do? It asks the question of how much room for improvement is there? What is the best we can do? It gives us something to aspire to. Thanks for listening. As ever, do leave comments, and I hope you'll join me again soon for another auto-contouring review.